Let's solve another thermodynamic problem involving a closed system power cycle. Let's look at a power cycle problem. 1 pound mass of water contained in a piston cylinder assembly undergoes the power cycle shown. For each of the 4 processes, evaluate the work and heat transfer, each in BTU. For the overall cycle, evaluate the thermal efficiency. So I have defined the system as the water molecules contained in this piston cylinder assembly. The cycle is shown here on a TV diagram, and from that I have deduced the following given data. State 1 is at 700 psi and it's a saturated liquid. State 2 is also at 700 psi, but it's a saturated vapor. State 3 is at 70 psi and has the same specific volume as state 2. And state 4 is also at 70 psi and it has the same specific volume as state 1. Now process 1-2 is isobaric, which means it's a constant pressure process. Process 2-3 is isovolumetric, meaning it is a constant volume process. Process 3-4 is also isobaric, and process 4-1 is also isovolumetric. We are asked to find the work and the heat transfer for each of the 4 processes, and then we're also asked to calculate the efficiency of this power cycle. So let's begin by finding specific volume and internal energy for each of the 4 states. Beginning with state 1, we're going to use the saturation table at 700 psi, and this is a saturated liquid. So state 1's specific volume is just V sub F, which is 0.02051 cubic feet per pound mass. And U1 is U sub F, which is 488.9 BTUs per pound mass. Now state 2 is also at 700 psi, so we're going to use the same line in the table we used for state 1, only state 2 is a saturated vapor, not a saturated liquid. So V2 is V sub G, which is 0.656 cubic feet per pound mass. And U2 is U sub G, which is 1,117 BTUs per pound mass. Now states 3 and 4 are both saturated mixtures at 70 psi. So again, in the saturation water table at 70 psi, we're going to grab a value for V sub F and V sub G and U sub F and U sub G, and these are going to apply to both states 3 and state 4 to help us find the quality and the internal energy. So let's look at state 3 quality. We know V3 is V2, and we have a value for that. So the quality at state 3 is just V3 minus V sub F over V sub G minus V sub F, all of these state 3 properties. We have those values and we get the qualities 0.1031. We can do the same thing for state 4. We know that the specific volume of state 4 is the same as the specific volume at state 1, which we know. So the quality at state 4 is just the specific volume at state 4 minus V sub F over V sub G minus V sub F. All of these values taken as state 4 values. And we get a very small number for the quality at state 4. It's almost 0. We could assume it to be 0 at this point, but I'm going to carry this value through just for a little more accuracy. So knowing the qualities at state 3 and state 4, now we can calculate the internal energies. The internal energy at state 3 is just U sub F plus the quality at state 3 times U sub G minus U sub F, all of these values being state 3 values. We have those, and we get the internal energy at state 3 is 357.97 BTUs per pound mass. Do the same thing for state 4. The internal energy at state 4 is just U sub F plus the quality at state 4 times U sub G minus U sub F. All of these values being state 4 values. We plug those in and we get the internal energy at state 4 is 273.0 BTUs per pound mass. So let's summarize what we've done so far. For each of the four states that occurred during the process, we have the specific volume and we have the internal energy. So now we can begin to calculate work and heat for each process. For the process 1-2, it's a constant pressure process. So the work is simply given as the pressure times the change in volume. And the change in volume is the mass of the system times the change in specific volume. So we know the pressure is 700 pounds-force per square inch. I'm going to go ahead and convert that to square feet. The mass of the system is 1 pound mass. And we have the specific volume at state 2 and state 1. At this point, we have energy units of foot-pounds foot-pounds-force, which I'm going to convert to BTUs. So I calculate that the work done by process 1-2 is 82.32 BTUs. Now we can calculate the heat transfer that takes place in this process 1-2 by writing an energy balance. We can say that Q is delta U plus W. And delta U is the mass times the change in specific internal energy. And W we just calculated. So we have a mass of 1 pound mass, a value for U2 minus a value for U1. And the work done during this process, 82.32 BTUs. And I calculate a heat transfer during process 1-2 of 710.4 BTUs. Let's go to the next process, process 2-3, and calculate the work. The work we know generically is the integral of P dV, and this is a constant volume process, so dV is 0. So the work done during this process is 0. Now we can calculate the heat transfer using our energy balance. Q is equal to delta U plus W. Well, we know W is 0. And delta U is just the mass, 1 pound mass, times U sub 3 minus U sub 2. We have values for that, and we calculate that the heat transfer during process 2-3 is minus 759 BTUs. Let's calculate work for the next process, process 3-4. Well, again, it's a constant pressure process. So the work done is the pressure times the change in volume, where the volume is given as, or the volume change is given as mass times the change in specific volume. So we have a pressure of 70 psi this time, and I'm going to convert pounds-force per square inch to square feet. Have a mass of 1 pound mass. We have a value for V4 and a value for V3. And again, I'm going to convert foot-pounds-force to BTUs. For process 3-4, I calculate a work value of minus 8.23 BTUs. Knowing that, we can use our energy balance to calculate the heat transfer. It's just the change in internal energy plus the work. And again, the change in internal energy is the mass times the change in specific internal energy plus the work term, which was a minus 8.23 BTUs. So I calculate that the heat transfer during process 3-4 is minus 93.2 BTUs. So let's calculate the work and heat transfer for the final process, which is process 4-1. It's an isovolumetric process, so there's no change in volume. And we know that work is the integral of P dV. Well, dV is 0 for this process. So the work for process 4-1 is 0. We can calculate the heat transfer for this process using an energy balance. And we know that the Q is just delta U plus W. And delta U can be written as the mass times the change in specific internal energy, which is U1 minus U4. We have all of these values, and we can calculate that the heat transfer is 215.9 BTUs. Let's summarize the process values that we've calculated. We have 4 processes, process 1-2, process 2-3, process 3.4 and process 4.1. We've calculated the work and the heat transfer for each of the 4 processes. 2 of the processes have 0 work. 1 process has positive work, 1 process has negative work. And some of the heat transfer terms are positive and some are negative. Now, if we sum all of the work terms, we will get the net work done by the cycle, which is 74.1 BTUs. And if we sum all of the heat transfer terms, we find that it is also sums to 74.1 BTUs. Let's explore this a little bit. Notice that they're identical, and if we write a simple energy balance for the cycle, where we're ignoring kinetic and potential energy effects, we can write, again, for the cycle, that delta U is Q minus W. Well, we have values for W and Q for the cycle, and so delta U is just 74.1 BTUs minus 74.1 BTUs is equal to 0. Well, it turns out that it's necessary for delta U to be 0 because this is a cycle. And remember, a cycle ends at the same state where it begins. So the completed cycle can neither accumulate nor dissipate energy. So this energy balance has to sum to 0. So let's calculate the thermal efficiency for this power cycle. I like to think of the efficiency of a power cycle as what I want divided by what it costs me to get it. What I want is net work from the cycle, and what I have to put into the cycle is energy via heat transfer. So Q, we'll call it Qn. Well, what is the net work? Well, it is the sum of all the work terms. We know that 2 of these terms are 0 and 1 of them is negative. But if I add them all together, that's the net work produced by the power cycle. Well, what is Qn? It is not the sum of all the heat transfer terms. It is the sum of the positive heat transfer terms because they represent the energy that I had to put into the system. The negative heat transfer terms represent the total amount of energy that was rejected to a low temperature thermal reservoir. So I'm only going to consider my input as the positive heat transfer terms. So we can put values in for all of these terms. And I calculate the thermal efficiency as 0.08 or 8%. And there's another interesting notation that you can make from this problem. Notice on the power cycle or the TV diagram that the processes progress in a clockwise fashion. And a clockwise cycle on a TV or a PV diagram represents a power cycle. It will produce work. If it were rotating counterclockwise, that would be a refrigeration cycle, and that would require work being input to this cycle.